So first scenario, we start out with 3 beakers, 3 dialysis tubes in it. Basically, it's trying to make sure you understand the difference between isotonic, hypertonic, and hypotonic. Right? So let's walk through each one of these just to make sure we've got it. Right? So it says 3 dialysis tubes contain 0.5% starch solution. Are placed in beakers containing various concentrations of starch as illustrated below. So in this case, all sort of opposite of what you did in lab, all the dialysis tubes have the same internal environment. We're changing the external environment, more like what we did with the potato cores. Note that the solvent is water and that the bag is permeable to water but impermeable to starch molecules, which means what? Starch is not capable of passing in or out of the tube. All right? So in the first scenario, you got 0.5% inside, you got 0.5% outside. What would you predict? Isotonic. Why? The solute concentration is equal inside and outside. Therefore, you would expect the water potential to be not necessarily 0. Equal. We would expect the water potential to be equal on both sides. So if this is 0.5% starch, we would, if there's nothing else there, say water's probably 99.5% inside and it's probably 99.5% outside. Therefore, the water potential should be balanced, should be equal. Therefore, representing that with arrows, I would expect water to be going out, and the arrow going in should be same size. I would expect there to be a fairly equal exchange of water. Right? I'm not having the starch exchange because why am I not worrying about the starch? It can't go in or out. It's impermeable. Right? With me so far. And this would be an isotonic situation. In the next scenario, I've got 0.5% starch in the tube, and it looks like pretty much distilled water in the beaker, 0% starch. Where is the greater water potential? It's outside in the beaker because there is no solute to bind the water. All the water is free. Inside, though it's not very much, it's 0.5% starch, that's going to bound at least some of the water. So relatively speaking, the water potential inside the tube is going to be less. So I would expect the majority of the water movement to go in which direction? I expect water to go in more so than the water going out. I expect there to be a greater movement of water inside and a less movement of water outside. Following? Yes or no? And in the third case scenario, 0.5% starch versus 1.5% starch, where is there going to be more water bound to solute? Outside, so the water potential is going to, outside it's going to go up or down. It's going to go down. We would expect a lower water potential outside, a higher water potential inside. Again, water will move in both directions, but I expect more of the water to go which way? Out. I expect a greater amount to go out compared to the amount going in. Any concerns on that part? That's base knowledge. So then there were some questions to respond to to that. The solution inside the tube is hypotonic to its surrounding. I know it's telling you where to use the term. In this case, it's saying refer to the inside of the tube. So if it's hypotonic, it should have less what? Less solute. Should have less solute. So in which scenario do we have less solute than the environment? 0.5 is greater than 0. 0.5 is less than 1.5. Yes or no? So I would argue that the correct answer in this case should be C. That's the case where solute concentration is lower in the tube than the environment. That would make it hypotonic inside the tube. Yes or no? All right. The net movement of water is from the bag into the beaker. Well, we already answered that. We just have to look at our picture. Where's the greater movement of water going into the beaker? And if we look again, that's going to be C. Okay? Water is leaving. Water tends to go from a hypotonic area to a hypertonic area. The solution inside the bag is isotonic. That's pretty straightforward. A, the dialysis bag swells. We'd expect B because there's a greater movement of water into the tube than out of the tube. The dialysis bag remains the same size. I would expect that to be A. And the water potential is higher inside the bag. Well, if we look at how we wrote it out, C again would be the scenario where the water potential is higher because you've got less solute, therefore more free water. Yes or no? Questions so far? This is a plant cell when initially placed in pure water has a solute potential of -4 bars and a pressure potential of +4 bars. All right, why am I getting a pressure potential all of a sudden? It's a plant, and it has what which creates pressure? Cell wall, which gives some resistance to the expansion of a membrane. That's where the pressure comes in. And that's the difference between the ones we did Friday and the ones that I asked you to do over the weekend, is we had to consider the pressure potential. All right? So let me do a simple drawing here. Whoops. So we've got a plant cell with this very thick cell wall. And according to this inside, what's the solute potential? What was it? -4 bars, which is just the unit for measuring pressure. And the pressure potential inside would be +2. Right, we've got a little bit of turgor pressure. So if that's the case, what's my water potential? Whoops. My water potential, the right symbol, psi, thank you. Water potential equals pressure potential plus solute potential. So in this case, water potential equals pressure, which is +2 bars, plus -4 bars for solute potential, yay. And of course, +2 plus -4 equals -2. So the overall pressure, the water potential of this system is -2 bars. Following it all? Any questions there? So, and it's placed in pure water. So the environment's pure water. All right? It's an open system, pure water. So my pressure potential is going to be what? 0. And my solute potential, if it's pure water, is going to be 0, because there's no solute present. So my overall water potential of 0 plus 0, 0. Right? Which way does the water want to move in this particular scenario? What's that? In or out. Moves from high potential to low potential, or low potential to high potential? High to low. Where's the higher potential? Outside. 0 is greater than -2. 0 is greater than -2, correct? So the net movement of water is going to be, there's going to be more water going in than going out. Water is moving from water potential of 0 to water potential of -2. Is that going anywhere? Water will continue to move in until what happens? Reach equilibrium. All right. Well, in this case, as water is gained, what factor is going to increase? Pressure. Pressure is going to go up. What's actually going to happen to solute if you keep adding more water? It's going to actually, percentage-wise, go down. All right. With me? All right. So if we go back to the questions, describe which way the water will osmose. All right. Well, in reality, water will move in both directions. But where will the net movement be? Into the cell. All right. So I want to note that it will move in both directions, as it always will, but net to the inside. In other words, more water is going to go inside than going to go outside. All right? Still with me? And we already asked this question a second ago. When will the net movement of water stop? When you reach equilibrium. Notice it says net movement will stop. And total water movement doesn't stop. You just get to a point where you have equal exchange. Water will continue to move in both directions at all points. All right? So when equilibrium is reached, what will be the approximate solute and pressure potential values? All right? We're still going to have approximately negative 4 bars for solute. Technically, it probably is going to drop to like 3.99, 3.98, 3.97. Because as water's being gained by the cell, there's going to be a slight dilution. Yes, no? But in this case, we're predicting it'll be a fairly minimal process. If we're going to go to equilibrium, what's the pressure got to go to? It's got to equalize the solute concentration. It's going to go up to a plus 4 bars. It's going to go from 2 bars to 4 bars. That gain of water is going to increase the pressure in the cell. Once you reach 4 bars, that counteracts, because 4 bars plus negative 4 bars equals 0. And remember, the outside environment was also 0. Now you're at equilibrium. Going anywhere? So as water comes in, pressure potential goes up, eventually to 4 bars, which makes this 0. Now you're at equal water potential. You're at equilibrium. Following it all? Take the next one, 3, a protozoan cell. So protozoan is like an amoeba, paramecium, something of that sort. They do not have what typically? So protozoans don't have cell walls. So pressure going to be a factor here or not? Probably not. All right. It is placed in a 0.5 molar sucrose solution at 27 degrees. Assume the cell has an internal potential of negative 2 bars. Okay. Solute potential of negative 2 bars. So again, let's sort of make a simple drawing here. Let's just say that's our little plankton there. Okay. It's got an internal pressure of, or excuse me, internal solute concentration of, yeah, it's got equal negative 2 bars. Okay. Environment is 27 degrees Celsius, and it has, what was it, 0.5 molar of, what was it, sucrose? So that's the information I've got so far. So protozoan placed in this situation has a solute potential of negative 2 bars. Because protozoans lack a cell wall, it cannot exist in a positive trigger pressure and always will have a pressure potential of 0 bars. So, in other words, if I want its overall water potential, I got to take pressure potential plus solute potential. It just told me its pressure potential is what? 0. And its solute potential, we've been told, is negative 2 bars. So its overall water potential equals negative 2 bars, right? Yes, no? Okay. So we then need to determine the water potential of the environment. I should have just stayed there. Water potential of the environment. It gives me some pieces, but it doesn't give me all the pieces. So I've got to, if I want to get the water potential of the environment, I got to go back to this equation. Again, we're in an open system, so the pressure is going to be 0. How do I calculate solute? Negative I just use that formula, negative ICRT. So this is sucrose, so again, the I is going to be 1. C, I was told C is 0.5. R is a given value. And T is 273 plus 27, 300, right? And if my old calculation is right, that comes out to negative 12 point something. Is that accurate? Negative 12.5 bars, approximately. Yes or no? So now I know the water potential. I now know from calculations the water potential inside this cell is negative 2. The water potential in this environment is negative 12.5. Going anywhere? That would tell me where's the greater water potential. Inside the plankton, negative 2 is a larger number than negative 12.5. So if there's a greater water potential inside the plankton, or the protozoan, which way is the water going to move net? Out. And this protozoan is going to do what? Shrink or shrivel. Right? Would this protozoan likely survive in this environment? Most likely not. It would dehydrate to the extreme. So, based on that, when the cell is placed in the sucrose solution, which way will the water osmose? Again, it will go both directions, but net movement out of protozoan. When will the net movement of water stop? When you have equilibrium. Another way to put that is equal water potential. What will be the appearance of the cell when equilibrium is reached? As we already said, it will be shrunk or shriveled or whatever word you want to use. All right. What will be the cell's approximate solute potential equilibrium? Whoops. So water is moving out. It's going to continue to move out till we reach what inside the cell? Which means you have to have equal water potential. So what's the water potential in the environment? Negative 12.5, so the cell eventually has to get to negative 12.5, which means this cell's got to lose an awful lot of water to get down there. This is almost certainly going to be a deadly environment for this particular organism. I'm not going anywhere there. Okay. So this will be, has to get down to about the same as the environment. What will be the cell's approximate pressure potential at equilibrium? In both cases, we had a pressure potential of 0. So there is no way to create pressure in this system, so it's going to remain at 0. Yes or no? With me, not with me? Is this worth walking through or not? So it's clearing up problems, or it's just repeating what you know? Okay. All right, so let's go to the second one. Just got to change sheets real quick. All right, so the next one says a plant cell. Bingo, plant cell means I got to account for pressure. That's the only real difference. So plant cells, I got to account for pressure. A plant cell with a rigid wall is placed in a 0.2 molar solution of salt. Okay, so let me just draw a plant cell again. Get that out of the way. I'm putting it into an environment of 0.2 m sodium chloride at 27 degrees Celsius. It's allowed to equilibrate. Assume the cell has an initial solute potential of negative 8 bars and an initial pressure potential of plus 2 bars. So pressure was plus 2, solute was negative 8. Its overall water potential is going to be negative 6. So this right now has a water potential of negative 6. Yeah? Based on this information, we're going to answer the following questions. So I know the internal water potential. I now need to calculate the external water potential. Is there any pressure in the outside? No information says there is. So we're going to assume again that the outside pressure is 0. Plus, then we go back to our good old friend ICRT, and we simply plug and play. Yay? So negative, in this case, salt has an ion concentration of 2. Solute we're given is 0.2. R again is a constant. And temperature is again 27 plus 273 or 300. If we do that calculation, what did I come up with? Approximately negative 10. Does that sound right? Did anybody do the math? Okay. So it comes out to about negative 10 bars. So based on this, where's the higher water potential? It's inside the plant at negative 6, and therefore more water is going to be going out than going in. Capiche? Yay, nay? Okay. So we have to go until water potential is equal on both sides. So we go back up to the ground. In which direction will there be a net movement of water? Out of plant cell. What will be the cell's approximate water potential at equilibrium? So at equilibrium, it's got to get to about what? It's got to, ultimately the cell has to equal what? About negative 10. It's got to match its environment. The odds of a cell altering the environment, not going to happen. The cell can't release or do something enough to alter the environment, so the cell has to adjust to the environment it's in. So ultimately, the cell has to find a way to bring itself in balance with the water potential of the environment, which is negative 10 bars. Okay? So at equilibrium, what has to happen? Well, we're losing water. So what happens to pressure? It goes down. It's going to go down to the point that pressure becomes 0. Following, in this case, we're losing water to the environment, and that's going to get the pressure down to 0, which means solute has to go from negative 6 to negative what? 10. We've got to drop that negative 6 down to negative 10 to bring it in balance with the environment. So the only way this cell can be in balance with this particular environment is to lose all its turgor pressure and drop its water potential to negative 10. Is that good for the plant? No. The plant's going to be wilting. Right? And the plant's not going to survive. This would be like you going away and not watering your house plants for several days. Right? If you got back in time and reversed the system and added water to the soil, then we could possibly still save the plant. But if the plant were to stay in this condition for several days, you're going to kill it. Yes, no? Does everybody get the idea why pressure would go to 0? Right. And then that means that if the pressure is gone, then you've got to equate the solute. You've got to equate the solute. Well, it'll be the cell's approximate pressure potential at equilibrium. 0 because we lost too much water to the environment. And this is a wilting plant that is not in good shape. Okay. One of the old-fashioned ways of preserving meat is curing it. All right? You can cure it with salt. You can cure it with sugar. Ham is the one that's traditionally cured with sugars, brown sugars, and those types of things. What the heck is coating meat with sugar or salt going to do? Pulls out the water, okay? Dries it, which prevents bacteria and decomposition. So it's a good preservation method. We're basically creating what type of environment by adding sugar and salt around the ham? We're creating a hypertonic environment around the ham, which forces the ham to give up its juices, which is good for preserving the meat and keeping the bacteria, because bacteria need moist environments to survive. Yay? Why will your favorite plant likely die if you apply twice the recommended amount of fertilizer? Not because it'll overgrow. Creates, again, similar, it creates a hypertonic environment. You double the nitrogen, double the phosphates, double the potassium, you're creating a hypertonic environment, which is going to draw water out of the plant and cause the plant to die, go brown. So when your dog goes out in the yard and pees in the same spot most every time, that builds up a high level of nitrogen in the soil, which creates a hypertonic environment, and thus you get those big brown patches in your yard. If you have a dog, you know what I'm talking about. Okay? Similar idea. Or if your dad asks you to spread the fertilizer on the lawn and you don't really pay attention to the setting on the spreader, or you keep going over the same spot multiple times, that's why you end up with these big brown spots in your lawn, and your dad will go nuts on you. Okay? No. All right. Questions?